Welcome to part 3 of this series on general relativity. Uh, Today, our topics are the constraint equations, the dominant energy condition, and apparent horizons. So, the motivation for this discussion starts with the Cauchy problem. So, the Cauchy problem for the Einstein equations says that we want to start with some initial data on a hypersurface M, a Riemannian manifold, and we seek a Lorentzian metric on the product that solves both the Einstein equations and matches the initial data. So this has obviously something that you'd want to do from a physical perspective, right? In most situations, you have some starting configuration, and you want to know how that configuration changes in time. And that's exactly what this seeks to do. Of course, with the complication being that in general relativity, the concept of time is not as simple. So, as I mentioned in part 1, when we talk about the Einstein equations, they're coupled to matter field equations via the stress energy tensor. So in what's going on here, really you're solving the initial data problem for this system that includes both G and your matter fields. So to simplify things, you could just think of the case where there are no matter fields. That's the vacuum case, in which case it is just a system of equations for this, trying to solve for this Lorentzian metric G. If we view this as a system of PDEs, as we must if we hope to solve them, the Einstein equations are second order in the time coordinate. So naively, you would expect that the initial data should be bold G and its time derivative. Remember, bold G is this Lorentzian metric. But if you think about it, it doesn't really make sense to want to specify bold G on this hypersurface M, because some of the components actually don't really mean anything. For example, if you look at, what would be like the time component of G, or like the normal component of G, that component doesn't really mean anything on its own, because you could just scale, right? You could just scale that new time coordinate in such a way that could be whatever you want. So because of that, many of these components have no real geometric significance. One can argue that a more geometrically natural choice of initial data would be just the induced Riemannian metric, which is just a regular G on M, and its second fundamental form K, that corresponds to the time derivative of G. So in other words, instead of looking at the Lorentzian metric G as being specified on M and looking at its time derivative, we're really just looking at the induced metric on M and its time derivative, which is roughly equivalent to second fundamental form, which again is a better way to think about it, because that's geometric. Okay, and so we define an initial data set MGK to be a Riemannian manifold MG together with some choice of symmetric 0-2 tensor K. And so as an initial data set, right, the K is just a tensor, but the way we think about it is, when we evolve it, that K is going to represent the second fundamental form of the slice in the Lorentzian spacetime that we are trying to build. Okay, well, that's not the only thing we have to adjust here. Certain components of the stress energy tensor, which remember is the same thing as the Einstein tensor for us, are entirely determined by G and K via the Gauss-Cauchy equations. In other words, it's not completely independent what's happening here. And thus, one cannot hope to solve the Einstein equations given arbitrary initial data. In other words, if I just give you any g and k, well, they might violate Einstein's equations from the get-go. So obviously, you cannot hope to find a space-time metric that satisfies them. So what do I mean that more precisely? Okay, so let's say E naught is a time-like unit normal to a space-like hypersurface in a space-time, and let's just take E1, E2, E3 to be tangent to M. So with this setup, we can compute that the Einstein tensor of the space-time metric, some of the components of that Einstein tensor are already determined by G and K. Specifically, if we take the 0, 0 component of the Einstein tensor and the 0i components of the Einstein tensor, you can see that they can be written explicitly in terms of G and K. And this, again, this is not anything exotic. This is just a direct consequence of the Gauss-Kadazi equations, which, of course, as you know, relate the curvature of this hypersurface to the ambient curvature, which also uses the second fundamental form. So in light of this, so that discussion was happening in a space-time, but in light of this, on an initial data set, which is just the data G and K, we're going to define these quantities to be mu and J. Okay, so remember, the Einstein equations, it identifies the Einstein tensor with the stress energy tensor. So this mu and J should be thought of as being components of the stress energy tensor. And what they represent here is essentially the energy momentum of whatever matter fields you have. So notice that I've sort of highlighted the R sub G term here. That's the scalar curvature. So in terms of analysis, and you can see that when you look at this quantity mu, the most important term is going to be that R sub G, which is a second order operator in G, whereas the K terms are a lot simpler. It's zeroth order in K, and the dependence on K comes in a very sort of simple way. So, I mean, this is kind of the explanation. This equation is kind of the explanation for why the study of scalar curvature is so closely related to questions that arise in general relativity. So in general relativity, we care about these quantities, mu and J, and the most significant term in mu is that scalar curvature. So so methods that we would use to attack problems in scalar curvature, or sometimes with some adjustments, can be used to attack problems with studying mu and J, and vice versa, right? If you if there are techniques from physics that were developed, right, then you can maybe specialize them to techniques that can be used to study scalar curvature. Okay, so these equations, these are called the Einstein constraint equations. So the Einstein equations, that's the full equations for the space-time metric G. The Einstein constraint equations, they constrain what the initial data can be given mu and J, right? Mu and J, again, coming from what the sources. All right, so now let's talk about how do you actually go about solving the Einstein equations. Well, Ivan Choquet-Bruhat, way back in 1952, was the first to prove a short time existence result for the vacuum Einstein equations. So that's the situation where the stress energy tensor is 0. Of course, mu and J are also 0, right? And under the assumption that the initial data satisfies the vacuum constraints. So we have to start with initial data that at least has a chance to solve the equations, and then we can solve the equations. So again, I mean, when I said mu and j are the energy momentum of the sources, I mean for the, the initial data for the matter fields would determine mu and j. Later, together with Robert Garrosh, she proved that there is a maximal globally hyperbolic solution. In other words, so not only do you have short time existence, but you can imagine what it means to basically make it solve the equations sort of, for as long as you possibly can until solving any further would break the globally hyperbolic condition, perhaps. The main technical difficulty in these in solving this is that the equations are diffeomorphism invariant, of course, right? They're curvature equations, and hence they're, as a consequence, they're not hyperbolic. But Choquet-Bruhat's groundbreaking idea was to use something called wave coordinates to break the gauge symmetry in order to produce an honest hyperbolic system of equations. So gauge symmetry is just the physicist's word here for diffeomorphism invariance. So we're breaking the diffeomorphism invariance by choosing special coordinates, right? So if you choose special coordinates, you no longer have, you can no longer make coordinate changes. So wave coordinates is they're like harmonic coordinates, right? Except they solve the wave equation instead of the Laplace equation. So many Riemannian geometers may be familiar with this idea from de Turck's trick, which of course is much later than 1952, for breaking diffeomorphism invariance. Right? It's a good place. It's a good application of the use of harmonic coordinates. For example, this is used to prove short time existence for the Ricci flow, among other things. So there, again, that would be more like a heat equation, of course, rather than a wave equation. Okay, so existence results for other matter fields followed, assuming that the initial data satisfies constraints arising from the matter field's initial data, as I mentioned. So unfortunately, if you want to prove such an existence result, of course, the matter field matters because that's its own set of equations. So every single result like that has to be a different result. But conceptually, the starting point was this original work in the vacuum case. Okay, in order to be a realistic matter field model, though, it should give rise to a realistic stress energy tensor. So we say that a spacetime N satisfies something called the dominant energy condition, or DEC for short. So I'll almost always say DEC to save myself some space in writing and whatnot. If, again, so remember the Einstein tensor essentially is the stress energy tensor. So this is, physically you should think of it as a condition on the on stress energy tensor, but of course mathematically it's just a condition on the Einstein tensor. So the condition is that the Einstein tensor G of UV has to be non-negative for all future causal vectors U and V. So, I mean, one way of thinking about this physical assumption is it's saying that the matter sources for Einstein's equations, they're not traveling faster than light or backwards in time as measured by any observer. Again, it's basically saying it's the closest. It's fairly close to trying to say that the sources for these equations, they're not sorry, they do not correspond to things with negative mass. Okay. this condition is stronger than the null energy condition that we stated earlier. Remember, the null energy condition was just that Ricci of UU is non-negative for all future null vectors. So this is much more general. Okay, so let's see what this dominant energy condition has to say about the constraints. So if M is a space-like slice of a space-time n with future time-like unit normal E naught again, and if n satisfies the DEC, then you can take any unit vector v tangent to M, and then E naught minus v will be future causal. So that means I can plug it in to this DEC, right? So E naught, both E naught and E naught minus v are both future causal. So G of that has to be greater than or equal to 0. And so what that's telling you is that, right, the G00, the 0, 0 component of G is at least is bigger than, or at least as large as the sort of the E0V components. In other words, the normal component is larger than any of the normal tangential components. So that's exactly how mu and j were defined, really. So it's, remember, mu is basically G00. So this implies that mu is greater than or equal to the length of j along M. So remember, mu and j, since they're determined by initial data, we can just characterize that in terms of initial data. So we say that an initial data set satisfies the dominant energy condition, or DEC, if mu is greater than or equal to the length of j. So, one thing I should mention is that, of course, I mean, the space-time version of the dominant energy condition implies this initial data set version. We call both of them DEC, but they are not equivalent, right? The space-time one is stronger because it implies the initial data set. The implication does not go the other way. Like if you have an initial data set satisfies DEC, that doesn't imply that the space-time that it's inside of would satisfy DEC. Anyway, the study of Einstein equations as a hyperbolic system is a large and active field of research, but in this series of talks, I want to focus our attention on initial data sets satisfying the DEC. Okay, so in other words, these are initial data sets that are physically reasonable. And one nice thing about this is that we can be completely agnostic about what type of matter fields we're interested in. We just care that they're matter fields that are physical enough that they give us DEC. And you can see that this equation, mu greater than or equal to length of j, right? It's a generalization of saying you have non-negative scalar curvature. In fact, it exactly says that non-negative scalar curvature in the case where k is 0. Okay, so we talked about null expansion in the last lecture. Now I want to talk about, well, what about if we just focus on what's happening in an initial data set? So let's say we have a complete non-compact initial data set, and we want to understand how the black hole region of its Einstein development, if there is any, intersects it. Well, since this is hard to do, we instead look at the trapped surfaces in M. As we talked about before, right, if you really wanted to know the black hole, you would have to know the whole Einstein development and then figure out where the black hole is. We got motivated from our last lecture. Maybe it's better to just think about trapped surfaces. And for many purposes, it's sufficient to only look at outer trapped surfaces. So given a surface in M with an outward pointing unit normal nu, so what is outward? Well, let's just suppose that, right, M has a non-compact end, and so nu just means it's pointing out towards that non-compact end. Then we can define the future outward null normal L plus to be E naught plus nu, where E naught is the future time-like unit normal in M, or 2M in the ambient space-time. Okay? So, in other words, having a choice of normal actually leads to a choice of future null normal. And the resulting expansion, theta plus, can be computed purely in terms of the initial data. So the null expansion here is the mean curvature of the surface plus the trace of k over that surface. So because of this, even though our definition of null expansion was originally for surfaces living in the space-time, we see that you don't actually need the whole space-time to define a null expansion. You could just be sitting in an initial data set. So initial data set is enough to define this. And we have some definitions here. We call it outer trapped if this theta plus is less than 0. I think for some reason I have subscripts on the plus. I don't know why. But anyway, if it's outer trapped if theta plus is less than 0, outer untrapped if theta plus is greater than 0, and marginally outer trapped if theta plus equals 0. So marginally outer trapped surfaces will be very important for us. So we'll use an abbreviation. We'll just call them MOTS for marginally outer trapped surface. Well, okay, now we'd like to compute the variation of theta plus if we vary sigma within the initial data set M. So what did we talk about in the last lecture? We talked about varying theta as you move along the shell of light in the space-time. Today, we want to talk about what happens if you vary sigma within the initial data set, which is very different. Okay, and it's not just going to be by shell of light variations or it won't just be shell of light variations or parallel surfaces, just any variation in the initial data set. So remember that theta is made up of h and trace k. Okay. So we need to vary h and trace k. So the first step is we want to compute the variation of h. So if you have first variation vector field given by phi nu, then we can compute dh dt. This is again a fairly standard computation in Riemannian geometry. The first line, right, is a generalization of the equation that we had in last lecture for the parallel surfaces, right? But the parallel surfaces is the case when phi equals 1. So we already talked about what dh dt is in that case. But in general, right, for a general first variation, you see that you get this Laplace phi term showing up. So that's the first equation. The second equation just follows from using the Gauss equations, right? So from the Gauss equations, we can get rid of Ricci nu nu and basically exchange it for K and Rm. So K is the Gauss curvature of sigma. Rm is the scalar curvature of M. And I don't know why I think I missed the subscripts on A and H there. So A and H, those are the second fundamental form and mean curvature of sigma. And as I said, the second line follows from the traced Gauss equation. So that's the H part. What about the trace K part? Well, it's straightforward but tedious to compute the derivative of the trace K term, right? I mean, it's not too bad, right? You're just tracing over sigma t. Sigma t is really the only thing that's changing. Well, in K, you're moving where you are in K, the K too. So, but you can compute this. Unfortunately, you get a rather ugly formula. So the formula is admittedly a bit complicated, but let me try to at least highlight some of the important stuff here. So there are some new terms that I introduced: W, Q, and tau. So W, Q, and tau, those all depend on what's going on sigma. W is basically, it just comes from K. So that's why you don't see it in the formula for dHdt. But the Q and the other terms sort of have analogs in the first in the equation for dHdt, and that's why I have some colors here now. So this tau times theta plus term, that's basically the generalization of the h squared term. And the Q sigma is the generalization of the other three colored terms I have. So I'll write it out explicitly. So Q sigma is equal to, well, the Gauss equation. So the Gauss equation, sorry, the Gauss curvature. The Gauss curvature, which was in the previous equation, is still here. The scalar curvature of M is now replaced by this term mu plus the inner product of J and nu. And the A term, the second fundamental form term, is now replaced by essentially K restricted to sigma plus A. So that term we don't worry about too much because it essentially has good sign for all the purposes that we're going to use later. So that's not a worry. And this scalar curvature term, which became this new term with mu and J, well, now we can see why the dominant energy condition is so useful. You can see that the DEC implies that this colored term is non-negative. So again, it will have good sign. So DEC kind of basically tells you that Q sigma is less than or equal to K, that the Gauss curvature. So I'm going to use this Q later on, but in your heads, just remember that the important thing to remember about it is that it's just some quantity that is less than or equal to Gauss curvature. So the Q is the most important term to look at here. Okay, and the W, while it doesn't matter to us, kind of the structure of the way W shows up does matter to us, and we'll see why. All right, so again, since this is a big thing to write down, it's an operator in phi. Obviously, it's a second-order elliptic operator, right? The main second-order term is Laplacian. We're going to call this operator L sub sigma of phi. It's the linearization operator for theta. Okay, so now let's talk about apparent horizons. We can define the weakly outer trapped region of M to be the region enclosed by either an outer trapped surface or a MOTS in M. Okay, so remember, these are the places where theta is less than 0 and places where theta is equal to 0. So you can actually think of it as it's the region enclosed by things with theta less than or equal to 0. And then we define the apparent horizon of M to be the boundary of the outer trapped region. So why is this called apparent horizon? Well, the outer trapped region and the apparent horizon can be thought of as a simpler stand-in for the intersection of M with the black hole region and event horizon respectively. So remember, we had this discussion about how trapped surfaces, we think of them as being inside the black hole. So that means this trapped region, could think of it as being inside the black hole, and the apparent horizon is the boundary of that trapped region. So it sits inside the event horizon. So the apparent horizon is again, it's kind of our stand-in for the event horizon, because the event horizon, like, we just can't really understand it very well. Whereas the apparent horizon is something that, at least according to this definition, we can kind of get a handle on it. And this is just repeating what I said, I guess. The advantage of these concepts is that they're directly determined by initial data, do not depend on the space-time development. So a theorem by Lars Anderson and Jan Metzger says that if an apparent horizon is enclosed by an outer untrapped surface, then it has to be a smooth MOTS. And so this is the reason why the MOTS are so important. So MOTS, remember, they're surfaces with theta equals 0. They're important because apparent horizons are MOTS. So, and now we present Hawking's theorem on the topology of black holes. I mean, so technically it's not really the topology of the black hole. It's really the topology of the apparent horizon. But it says that a smooth apparent horizon in an initial data set satisfying the DEC has to be a topological sphere. In other words, black holes should be spherical. So this theorem was generalized to higher dimensions by Greg Galloway and Rick Shane. They showed that in higher dimensions, the analog of a apparent horizon has to be Yamabe positive, which is a topological condition. And the Yamabe 0 case was fully ruled out by Galloway. And so I'm gonna for the rest of today's talk, I'm gonna summarize a proof of Hawking's theorem, and I'm gonna give essentially the proof that that Galloway and Shane gave. So Hawking's proof is a little bit different, but it's sort of the same spirit is going on, I guess. So, so let sigma be a smooth apparent horizon. Then it has to be a MOTS. That's meaning that theta is 0. And there are no surfaces with theta less than or equal to 0 that enclose it. Because all the surfaces with theta less than or equal to 0, those are all in the trapped region. And the apparent horizon is at the boundary of the trapped region. So this is the important condition, basically, that it's not just a MOTS, but in some sense it's the outermost MOTS. Like there are no MOTS that outside of it. Okay, although L sigma is not a self-adjoint operator, there does exist a positive eigenfunction phi with real eigenvalue lambda, and that is a much more well-known fact in the self-adjoint case, right? In the self-adjoint case, you can find the smallest eigenvalue using like Rayleigh quotients, and then you can also separately prove that the eigenfunction that goes along there is positive, and it's one-dimensional. The eigenspace is one-dimensional. Okay, but in general, when it's not self-adjoint, you can still find a positive eigenfunction with a real eigenvalue. So this more general fact, you can't do it with Rayleigh quotients, but you can still. There's still a proof using the Krein-Ruttman. The Krein-Ruttman theorem is basically the result, and they and this positive eigenfunction, we call it the principal eigenfunction, and its eigenvalue is real. The principal, it's also called the principal eigenvalue as well. Okay, so the idea is to use a variation whose first variation vector field exactly corresponds to this principal eigenfunction. We like this principal eigenfunction because it's positive, so that means it's an outward variation, and it's an eigenfunction, so that means it's easy to compute L sigma of it. So the variation of theta, d theta dt, right? It's given by L sigma of phi. It's an eigenfunction, so we just get lambda phi. Okay, so if lambda is less than 0, that would mean that for small t, the sigma t encloses sigma because it's an outward variation, and theta would be negative. But that's a contradiction because we're not allowed to have negative theta surfaces that enclose sigma. Okay, so the consequence is that lambda is greater than or equal to 0. All right, what can we get out of lambda being greater than or equal to 0? Well, let's rewrite things. So 0 is less than or equal to lambda. Lambda, by definition, is L phi over phi. which is fine because phi is a positive function. That's the same thing as, by definition, that's 1 over phi times d theta dt. Okay, and then the next line, though, is not obvious, but if you write out d theta dt, the formula we had before, it's not this one, but we can sort of massage that formula to get this one. So if you take that formula that we had for d theta dt and then divide by phi, and you just start rearranging some terms, you can get it to look like this. So dividing by phi is important here, right? Because I have grad log phi, which wouldn't make sense otherwise. Okay, and that's actually why I said that the way w appears in that expression is important, because that's what allows us to do this rearrangement. So let's take this inequality and integrate it over sigma. And we know that sigma is a mot, so it has theta equals 0. So the divergence goes away because we're integrating over a closed surface. And the next term has a sign, so we can ignore that. And theta plus is 0, so we can ignore the taus. So the only thing that really matters now is just the q. And I'll just repeat what the q was. This is our definition of q. And as I said, that's less than or equal to the Gauss curvature, thanks to the dominant energy condition. So the dominant energy condition is what we invoke at this step to get that last inequality. And now, by the Gauss-Bonnet theorem, sigma has to be a sphere or torus, because it's an orientable surface whose integral Gauss curvature is greater than or equal to 0. We know the only possibilities for that are sphere or torus. So it remains to rule out the torus case. So in the torus case, integral k is 0. So these inequalities become equalities. That means the lambda has to be 0. And for this, we're going to follow the argument due to Galloway. Okay, so this is actually maybe the most, there's a bit of a technical bit here that we have to go, but if you just accept that, we'll be okay. But so let's see. How do we rule out the torus? So in this case, that principal eigenvalue is 0. So in other words, that means we have a one-dimensional kernel. It's spanned by a positive function. And one can prove that, well, the adjoint will have that same property. So remember, the adjoint is related to the image of L. So from this, you can see that the constants form a complementary subspace for the image of L. Okay. So L has a one-dimensional kernel, and this one-dimensional co-kernel, basically. But we can have it so that that complementary subspace is exactly the constants. Okay, remember, L is effectively its linearization of the operator theta on nearby surfaces. So we want to invoke the inverse function theorem for theta. Okay, so let me just remind you. So let's think of a simpler situation. If L were an isomorphism, then the inverse function theorem basically says that we can solve for prescribed theta. Right? For any small prescribed theta, we could solve it. That's what the inverse function theorem will give us. Well, in this case, L is not an isomorphism, but it's sort of, it's missing something in the kernel. It's missing something in, it has a one-dimensional kernel, and it's missing something in the image. So, but we still want to invoke the inverse function theorem. So the way we do that is we introduce an extra degree of freedom. So essentially, we take out the kernel, put in an extra parameter in the domain, but in the image, we use that extra parameter to get back surjectivity. So, I mean, if you're familiar with these kinds of arguments, maybe that makes sense. Otherwise, maybe I'm just talking nonsense. But what that means is that you cannot solve, say, for theta plus equal to whatever you want, but you can solve for theta plus, prescribed theta plus modulo a constant. So if we basically want to solve for theta equals 0 modulo a constant, it means we can find theta equal to a constant. And that's what happens here. So this implies that there exists an outward variation sigma t such that theta is constant for each t. Right? We don't get to choose what the constant is. That's where we lost. Right? That's where this degree of freedom is coming from, is that we don't get to choose what theta is, but we do get to say that theta is constant. Okay, but on the flip side of that, we do know that we can accomplish this with an outward variation. In other words, we know that the solution that we're interested in is not just going to be the trivially just the original sigma we started with, because while we introduced that extra degree of freedom in both the domain and the image. Okay, so we can essentially force sigma to move off and give us an outward variation. Okay, so that's the part I'm not maybe explaining in detail. But from here, I can describe the rest of the argument in detail. So since sigma t encloses the apparent horizon, right, we can't have theta less than or equal to 0 because it's an outward variation, right? And we know that anything with theta less than or equal to 0 is in the trapped region. And here's where being constant matters, right? If you're not theta less than or equal to 0 and theta is constant, that actually means that theta is strictly greater than 0. So that's really kind of where the constant part is being used, right? That it's not less than or equal to 0 everywhere, so it's greater than 0 everywhere. In fact, constant. But okay, so if we define our first order variation vector field given by this this family sigma t, okay, except now we're going to do it at every t, not just at t equals 0, then the formula that we had from above gives us this. So this is the exact same inequality that we had before, saying 1 over phi d theta dt is less than or equal to the divergence term plus the Gauss curvature, and then minus tau theta plus. So the tau theta plus is a little bit annoying because we don't know that theta plus t is 0 anymore. We only knew that theta was 0 when t equals 0, but we don't know what it is in general. So that's the only thing getting in our way here from getting our contradiction. But we can deal with that using an integrating factor. Basically, choose a big C that bounds tau times phi, which is possible because remember we're only just looking at maybe a small family of times t. So if you just choose a big constant c that bounds that, then we can use an integrating factor, right? And instead of saying d theta dt, I take ddt of e to the minus ct times theta, okay, and then we get the inequality that we want, right? So I mean, if you just compute that out, you can just see that the capital C is letting us ignore that tau term. Okay, now we can argue as before where we integrate. So integrating this over sigma, that makes the divergence term go away. The integral k term now is 0 because remember we're talking about the torus case, trying to rule out the torus. So the right hand side is 0 after you integrate. This thing being multiplied on the left is positive. So what that really tells you is that ddt of e to the minus ct theta t is less than or equal to 0. Right. I mean, I guess I'm also using the fact that theta is constant here again to say this. But now, okay, well, remember, now that's, of course, again, contradicts the fact that theta had to be positive for all t greater than 0, right? Because now I've seen that the derivative is less than or equal to 0, and we started at 0. So that's it. That's the whole proof. Okay, so just some quick words about the legacy of this is that this Hawking's work was an important precursor to the work of Shane and Yao on positive scalar curvature in the late 70s. Again, the Hawking's argument is actually a little bit different from what I presented, but this important idea of using the Gauss equation to rewrite the Ricci new term was present there. To rewrite that in terms of the Gauss curvature. But then Chen-Yao also used similar computations to derive topological restrictions for positive scalar curvature, and they further applied those ideas to the positive mass theorem, and that's going to be our topic for our next lecture, lecture 4. One thing I want to emphasize about what we did above is that in this proof above, we saw the usefulness of L sigma having non-negative principal eigenvalue when sigma is a Motz. So this condition has a name. When this happens, we say sigma is a stable Motz. The reason why we call it a stable Motz is basically an analogy to minimal surfaces. It generalizes the usual definition of a stable minimal surface. So the reason why it's called a stable minimal surface is that stability is related to the second variation of area. So that's why I say this is definitions by analogy, because for a Motz, area is not directly relevant, right? So stable, being a stable Motz does not come from being, it's not related to any kind of second variation property. It's only related to being the first variation of theta. But that's enough to make this analogy useful. Okay, so in our next talk, we will get into the details of that.